Hello, eager young minds. Today we are going to solve the problem of a cantilever bar subjected to uniformly distributed load by Rayleigh-Ritz method. So it's a method that hinges on the concepts of strain energy, work done, potential energy. Okay. So without further delay, let us solve this problem in a step-by-step fashion. So to begin with, just imagine we have got a cantilever bar. You can call this as a rod if you wish. So this is a cantilever bar. And let me define the geometric properties of this cantilever bar. This bar has got a length of magnitude L. It has got a cross-sectional area of magnitude A. Okay. So I have clearly defined all the geometric properties. So once you define the geometric properties, the next thing that you do is you try to define the material property. And the material property that we are concerned about, since it is a bar, the primary material property that we are concerned about is the Young's modulus E. So I'm not mentioning the units. I hope that by this time you should become conversant with all the units. You should have, I guess. Okay. Now, what is the stuff that this bar is being subjected to? Okay. This bar is subjected to a uniformly distributed axial load that is represented by this small red arrows. And the magnitude of this uniformly distributed load, that is the rate of loading, is given as Q. Its unit can be Newton per meter or Newton per centimeter or Newton per mm. Okay, you just have to take care of the units when you do this problem for real-time example problems with the real-time values. You just take care of the units. Okay, fine. Now, what is the first step to solve this problem by Rayleigh-Ritz method? The principle of minimum potential energy. Okay, the first step always is to assume a trial solution. So step number one. This is step number one, is you always start by assuming a trial solution. And what is the trial solution that you are interested in? The trial solution is u of x is equal to a naught plus a1x plus a2x square. Now you may ask me this question, why do you stop at a2x square and why not go for a3x cube? Or you may even ask me this question, why is that you are not assuming a linear trial solution? For all these things I have answered already. I have derived the governing differential equation. I will give the link in the description below. You will know why we have to assume the trial solution of order 2, because why we have to assume a quadratic trial solution, because the governing differential equation of this bar has the order 2. Okay, so if you I can write the governing differential equation just as a reminder. It is ae into d square u by dx square plus q is equal to 0. If you integrate this equation, now how do you get this equation? You may also ask this question out of curiosity. I have derived this equation. You can check it through. I will give the link in the description below. If you integrate this governing differential equation 2 times, you end up with this trial solution. So simple as that. So there is a perfect methodical and systematic manner in assuming this trial solution. Okay, hope that is clear. The second step is to apply the boundary condition. So let me do the second step now. The second step, number 2, it is to apply the boundary conditions. So BC stands for the boundary conditions. So what are the various boundary conditions? At x is equal to 0, that is u of 0, which means at x is equal to 0, there is not going to be any displacement because it is fixed. This is first boundary condition. What is the second boundary condition? The second boundary condition is the strain, which is given by du by dx, which is change in length divided by original length, but you are trying to define the strain at a point. The strain at x is equal to L, which means you are talking about the free end of the bar, is 0. Why that is the case? Well, you know that there is not going to be any strain when a person clings onto the ceiling and his friend is clinging onto the foot of the first person, and the third person is going to cling onto the foot of the second person, and the fourth person is going to cling on to the foot of the third person. You see, there is not going to be any strain here. The strain is 0. So it is exactly for the same reason why you put the strain here as 0. So both these conditions are almost similar. Okay. So let us try to apply this boundary condition. At x is equal to 0, the value of u is 0. So that should give a naught to be 0. So that is quite straightforward, because when you put x is equal to 0, this term vanishes, this term vanishes, this term is 0, so a naught is 0. Okay, fine. Let me apply the second boundary condition. In order to apply the second boundary condition, you have to find du by dx. So what is du by dx? It is a1 plus 2a2. Of course, you are applying the boundary condition at x is equal to L. It is 2a to x, so in the next step, it's going to be a1 plus 2a2. Instead of x, you have to put L, okay? Because you are trying to define the boundary condition at x is equal to L, it's going to be 0. So you can find a1 in terms of a2. So a1 is equal to minus 2a2L. All right? Now, the third step is to modify the translation, because since you have got the value of a naught, which is 0, and you are also able to get the value of a1 in terms of a2, you plug those values in the translation and you get the modified translation. So let me do step number 3 here. So step number 3 is to modify, M for modify the trial solution. MTS, it stands for modify the trial solution. Okay. So let us modify this trial solution. U of x is equal to a naught is 0. A1 is minus 2a2L into x plus a2 x square. All right. So u of x is equal to, you take the value of a2, it's common outside, and you will be getting x square minus 2lx. So this is the modified trial solution. So let me put a box there. So this is the modified trial solution. I can call this as a star equation. So you look at this equation. This equation almost gives you the value of displacement of this bar at any point. Okay, at any point of the bar, at x is equal to L by 2 or at x is equal to L by 3, at any point in the bar you can tell the value of displacement. The only thing that hinders us from finding the values of displacements is the value of A2. Now you're going to find the value of A2 by using Rayleigh-Ritz method now. So let me move on to step number 4. So here we go. This is step number 4, is to find the strain energy. Strain energy is denoted by the notation U. So let me write the formula for strain energy. Strain energy for a for a bar subjected to uniformly distributed load, it is AE by 2 integral over the limit 0 to L du by dx the whole square. All right. So we know what is the value of U. It is A2 into x square minus, that is minus 2lx. Sorry about the terrible handwriting. That's right. So you can find what is du by dx. What is du by dx? It is A2 into 2x minus 2l. Maybe you want to pull this 2 outside, so that becomes 2a2 into x minus l. All right. So in the next step, it is going to be AE by 2. And I'm going to take the square directly. So let me do that. So if you do the square, so what is going to happen is if you pull the 2 outside, and you take the square. Already a2 is there, it's going to be a2 square, and 2 square, it is 4a2 square into x minus l the whole square. It's a square plus b square minus 2ab. That's right. So that's the value of strain energy. I mean, that's the expression for strain energy. So let me, no, I have to integrate this, right? So you are going to integrate this with respect to dx. Now, if you're wondering how this formula comes, guys, I have made a separate video for that. You can check it through. I can also give that link in the description below. How do you get the expression for strain energy of a bar subjected to uniformly distributed load? Okay, fine. In the next step, let me integrate this and substitute the limits directly so you can save some time. So let me integrate. Even in your examination, you should be able to integrate and substitute the limits directly. Maybe this 4a2 square I can write here, put a box. So let me integrate and substitute the limits directly. So here we go. All right. So integral of x squared is x cubed by 3. It's going to be L cubed divided by 3. Plus integral of L square is L square x. So if you substitute the limit, that becomes L cubed. Minus integral of 2Lx. That will be 2 into L into x squared by 2. Upon the substitution of the limits, it becomes L cubed. 2 in the numerator and the 2 in the denominator, they cancel out. Get rid of these two terms. So in the next step, strain energy U is equal to 2 by 3 AE into A2 square into L cube. Right. So 2 by 3 AE into A2 square into L cube. So that's the expression for strain energy. So that is our step number 4. Step number 5 is to find the work done. So let me do that. Step number 5 is try to find the work done. So let me go back to the physical scenario. It is a cantilever bar that is subjected to uniformly distributed axial load. Let me represent the uniformly distributed axial load by this yellow little arrows here. What is work done, by the way? It is force into distance traveled by the force. So here we go. Let me find the force acting in this region. The force that is acting per unit length is Q. So what would be the total force that is acting over a region dx? That's very simple. If the force acting is Q for 1 unit length, then for dx, what would be the force? So that will be Q into dx. Sort of like if 5 chocolates cost 10 rupees, how much would 8 chocolates cost? Something like that. A simple, maybe a silly example, but anyway, it helps us to get across the concept. So the force clearly is Q into dx into distance traveled by the force. Because of the application of the forces, this point travels a distance along the x direction. Okay, maybe I can represent that by blue for clarity. Along the x direction by an amount u. So the distance traveled by the force, because there is a separate video on work done also that I have made. You may also want to check through that video in order to wrap your mind around some of the intuitive concepts of work done. So I will also give the link in the description below. So Q into dx into u, force into distance traveled by the force, right? So that is work done by this force given by the shaded region here. You can also define work done for the next shaded region, and also define work done for the next shaded region. And all you have to do is sum all the work dones. You will get the total work done. But Newton is saying You can sum it, but I have a shortcut for summing up all the forces, and that shortcut is the integration. So Newton used to write the letter S this way, so it's integral over the limit 0 to L, which means that you are summing up all the work done by all the small forces concentrated in that small region. Okay, so that is total work done. That's right. So let me continue. It is integral over the limit 0 to L. Q is a constant. I can pull it outside. What is U, by the way? It is A2 into x square minus 2lx into dx. All right, so that's our star equation, right? X square minus 2lx. So let me integrate and get the value of work done. It's Q into A2 into, let me integrate and substitute the limits directly. It's going to be L cube divided by 3 minus L cube. So in the next step, it's going to be minus Q by 3 into A2. So it's going to be minus 2 by 3 into Q into A2 into LQ. So that's the expression for our work done. So you may want to double check this and see how I get the expression for work done. So you take the LCM, it's going to be minus 2L cube by 3 into Q into A2. Fine. That is step number 5. And step number 6 is find the potential energy. Very simple. Potential energy is equal to strain energy minus work done. You have already got the expression for strain energy. Take it and put it here. You already have the expression for work done. Just move it. Mathematics is just like moving objects. So strain energy is 2 by 3 AE into A2 squared into L cube. 2 by 3 AE into A2 square into L cube. That's right. Minus work done. You have the expression for work done, and that is minus into minus. It becomes plus now. It's plus 2 by 3 plus 2 by 3 Q into A2 into Q into A2 into L cube. So that is our step number 6. It is to find the potential energy, which is strain energy minus work done. So you want to find the concept behind this. Then you have to watch the video on principle of stationary total potential. I'm sorry I'm mentioning so many videos here, but if you are not familiar, you can check it through at the privacy of your room. Fine. Then step number 7, it is to apply Rayleigh-Ritz method. So R, it stands for the Rayleigh-Ritz method. So I'll tell you what is Rayleigh-Ritz method. That is the principle of stationary total potential. You differentiate the potential energy with respect to the constants and equate it to 0. Of course, we have got only one constant that we want to differentiate it with, that is with respect to A2. So let me do that. If you do this and differentiate this equation with respect to A2, what is that you're going to get, guys? You're going to get 4 by 3 AE into A2 into L cube. And if you differentiate this term, second term, it is 2 by 3 Q into A2 into L cube. I'm sorry, I just made a mistake. If you differentiate this with respect to A2, you'll be getting 2 by 3 Q into L cube, and that is equal to 0. So you can cancel L cube, divide L cube on the left side and the right side, and also divide by 2, so you get 1 here. Fine. So now you also multiply by 3 on the left side and the right side, you cancel that out, so you get the value of A2. So what is the value of A2? It's very simple. A2 is equal to minus Q divided by 2AE. That's it. You get the value of the constants. So this is Rayleigh-Ritz method. It's very cool. Now in the next step, the last step, step number 8, Once you get the value, you substitute the value of A2 in the star equation, which is the modified trial solution. What is the modified trial solution? U of x is equal to A2 into x square minus 2lx. Now you have the value of A2. It's going to be q divided by 2ae. Let me hit that with minus sign, so you get 2lx minus x square, which is the same as the exact solution, same as the exact solution that is obtained by solving the differential equation. So which means that the concept of Rayleigh-Ritz method, which is the principle of total minimum potential, works really well. It goes hand in hand, shoulder to shoulder with the method of solving the differential equations. Hope this may be useful. So the first step is to assume a trial solution. Second step, you apply the boundary conditions. Third step, you find the strain energy. Fourth step, you find the work done. Fifth step, you find the potential energy. I'm sorry, that is step number 6. You find the potential energy. And step number 7, you find the Rayleigh-Ritz. You apply Rayleigh-Ritz method to squeeze out the values of the constants. Once you get the values of the constants, you plug those values of the constants back in the trial solution to get the equation for displacements, which is exactly the same as the equation for displacement obtained by solving the governing differential equation. Hope this is useful. Thank you so much for the patience.